Daniel Bergh. Yes, thank you very much for this invitation and a very nice conference. This is work in progress with many people, and my talk will have three parts. So I will first describe this theorem. And then try to give two applications of this. One is to geometricity of some categories. Where X is smooth, the rim of the stack. And the second unrelated application will be the proof of the conjecture of Elkin and Schindler about categorical motivic data functions. So, okay, so let me start with motivation. I will recall the usual weak factorization theorem in algebraic geometry. So what does it say? It says if you have two birational smooth and projective algebraic varieties, the birational isomorphism between them, then you can decompose this birational map into a zigzag of honest maps. Well, that's not a surprise, but the key statement is that the solid errors are the maps which you can really understand and control. Well, these are all blow-ups with smooth centers. So now let me ask a question here. So suppose I modify my situation a little bit. So I have x and y, but there is a finite group action on x. And there is a y, and there is a field isomorphism given of I take rational functions on x and I take the invariance. So this is a subfield. I'm given an isomorphism with the rational functions on y. Right? In other words, I'm given some finite rational map from x to y, which is generically the quotient Body group. Now, can I construct some kind of zigzag here, which will be honest maps which I can control? Okay, so the question is there anything like weak factorization in this case? So this is the question I asked specialists about a year and a half ago by email, and no one answered me. And then half a year ago, there appeared a thesis of Daniel Bergh which answers this question. So this is what I want to talk about. But for this question, let me give you a concrete framework. So example, it's the topic of Mackay. It's the following. So suppose we have x smooth with an action of g, and you take the quotient, which is not smooth, and then you take the resolution of the quotient. And Mackay suggests that we study equivariant geometry on x and try to relate it to the usual geometry on y. By geometry, I mean, for example, derived categories. And to do this, to be able to do this in some manageable way, you need to fill this diagram somehow. So you need to put here something that would map both to x and to y in a controllable way. Right, that's it. variant of this question. So you want these arrows to be controllable.
So can you take the fiber product? Can you take the fiber product?
Well, it will not be smooth. So
one is a Crépin resolution?
Huh?
So it's a Crépin resolution or any resolution?
Any resolution. So that thing here should be smooth and the map should be controllable. That's a variant of this question. Now the first naive thought that comes to your mind is the following. Well, let's try to blow up X equivariantly until the quotient of the blow up becomes smooth. Right. Well, that's not possible. There are easy examples where just cyclic group acting on A2, where after one blow up you reproduce the same singularity. So that doesn't work. And here is the theorem of Bergh, which says you can do that if you allow to fill this with a Dewey-Mumford stack, not a global quotient. So I will state Daniel's theorem minimally just for the purpose of this too, but it's an extremely general theorem. So suppose that X is a smooth Dewey-Mumford stack. So, let's take its coarse moduli space. I'm not sure when it exists or not, but let's assume for simplicity it exists. Well, I'm thinking of this X as being my global quotient stack, and then this coarse moduli space will be the honest quotient. And then he says that there exists another smooth Dewey-Mumford stack X bar with a map M such that its coarse moduli space is already smooth algebraic space. And more importantly, and so that will be a resolution actually of this single one. The following properties. So the horizontal map F is a composition of what Daniel calls stacky blow-ups. So stacky blow-ups, it's either a usual blow-up with a smooth center, or it could be a root construction or a rooting. So if you have smooth stack and you have a smooth divisor, you can construct another smooth stack, which is taking the rth root of this divisor, and it maps to y. So this is an isomorphism of stacks away from the divisor D, and over D you get some Europe stuff. Okay, so really every step, therefore, F is a composition of steps which you really can control.
Sorry, is this last thing something like the branched cover, and then you take the quotient by the...
Yeah, so you take the cover which is branched along the divisor D, right? And so there will be a cyclic group action, and you consider this as a step.
And a divisor is really a substep?
Huh?
A divisor is a...
When I write the divisor in a stack, it's always a substep. Right. So second, as I said, the coarse moduli space is smooth.
Should it be clear?
Huh?
This is smooth.
I'm sorry? And you can say what G is. So G is a composition of a jerk So this will be a germ, so going to some x double prime. And then this map to the force modular space is a composition of root stacks. So this is rooting. And what's more important is that, so here you choose a divisor with normal crossings, and so you root with respect to each component of this divisor. Since the divisor has normal crossing, it doesn't matter in which order you do it, and the result is still smooth. So this is really also something you can control. Now, if you started with an orbifold, if x was an orbifold, generic stabilizer was triple, then there is no Jorge part here. That will be, this x prime will also be an orbifold.
So is it some kind of strong factorization?
Well, it's not as strong because I don't choose this model. You see, this is, if I choose some resolution of this thing, then this resolution will be connected to this by the usual weak factorization.
So is the choice of the root stacks unique?
Well, he gives an algorithm. He has an algorithm which is runs. It works actually over any base. Because you don't need resolution of singularities because you start with something smooth, and then he has an algorithm how to do that. So
sorry, so do you need D to be divisible by R or the divisor?
No.
no, that's the point.
Yeah, okay.
And sorry, this bottom map is a resolution of singularity.
The bottom map will be a resolution, right? So, well, there are some issues like this may be an algebraic. So you may have started with a projective. Do we want to state, meaning that the force modular space is a projective variety, right? And then I think that in this case this will be a projective also. So projectivity is preserved under stacked blow-ups. So what's important for me here, I just want to remind you, I will be watching the derived category. So those stacking modifications, they allow you to control the change of the derived category. Yeah, I think this is an amazing result which should have many, many applications. And so I think that what I'm talking today is just a sample of possible applications of this. So recall semi-orthogonal decompositions. So if you have a, say, stack or smooth stack or smooth variety, and you have a four-dimension R smooth subvariety, you can take the blow-up. And you have this picture, and the category on the blow-up decomposes in a well-known way. So it has a semi-orthogonal decomposition. One of the components is just the category on X, and you have several times the category of the center appearing. And the number of times is R minus 1. And you also have a similar decomposition for rooting. So if you have Y, you join the R root of the divisor D, equal to Y. Then the category here also has, in fact, as Daniel explained to me, this rooting is, formally looks exactly like the blow-up, and so for him there's no difference between blow-up or rooting, and things can be proved simultaneously. So the derived category on upstairs is has a semi-orthogonal decomposition. Well, one of the components is that of Y, and then you've got several. Let me call the divisor. It's curly D, and again, so R minus 1. All right. So now applications. The first application is to geometricity of categories. So let me. I'm not sure the terminology is here well settled. But let me remind you some sort of embedding of commutative algebraic geometry into non-commutative algebraic geometry. So, non-commutative algebraic geometry studies categories which are called saturated or smooth and proper. But what they are actually, they are the categories of perfect modules over some DG algebra. So this is a triangulated category, and the DG algebra has to satisfy two properties. So A is DG algebra, which is smooth and proper. So proper means that A is just a perfect complex of the base field, which is, I work over C, I should have said in the beginning. So, meaning just that the A has finite dimensional cohomology, and the smoothness for A means that A is a perfect bimodule over the enveloping. And there is an embedding of commutative algebraic geometry in the non-commutative. So if you have X, which is smooth and proper variety, then the category of perfect complexes on X, which is the same as the category of coherent sheaves, will be equivalent to one of these, or of A, where what's A? So you need to choose a generator for this category, and A will be then R and of E, where E is a generator. For the category of X. Okay, so that gives you the embedding, and for non-commutative geometries, well, there is no geometry is a question, but you think of this as being non-commutative compact manifold. Now, at this point, I want to advertise another piece of work by a young mathematician. He's another collaborator of mine, and so as you see here, there is DG. So DG enhancements come into the game, and they're essential for doing anything that you want to do in non-commutative geometry. And so this equivalence provides a nice dictionary, even if this embedding is in some sense an equality. We don't know that there are non-commutative motifs. We just don't know examples of varieties with examples of categories which are not geometric. But even if everything was geometric, this is still a very useful dictionary. It's just another way to look at X from this point of view. But this dictionary was not well developed, and there were really nasty and sort of annoying problems when you try to prove that something that looks obvious. And the problem is that when you apply a derived function, you need to take a resolution either injective or projective or flat. And when you take a composition of derived functions, you need to change your resolution, right? And that's a big, nasty problem. For example, if you read Hartshorne's book, Residues and Duality, then he maybe was the last honest man to write about this, and he said all results are conditional, because you really have to sit down and check the factorial identities, and the identities are preserved by other functors and so on. So I think that now we have a solution of this problem, because Olaf Führer, he came up with a factorial enhancement, canonical factorial enhancement, which should solve all those problems, so that should help to develop this dictionary. Basically, what he says is that if you have a complex C, then it has a canonical injective resolution, and this arrow is a DG function. In other words, here you can look at the DG endomorphisms of this complex, and so it lives in some DG category, and taking an injective resolution is a DG function. So that should sort of take care of all the difficulties. Oh, he's writing this down now. What? Oh, Olaf Sture. Okay, so here's the definition of a geometric category. So we say a triangulated, when I say triangulated category, I now will always mean something like perf of A. C is geometric if C is a semi-orthogonal summand in perf of A, where A is smooth and projective. I'm not sure if this is Olaf's definition or that may be, some people call it a stronger geometric. Doesn't matter. So why? Let me just point out why we may be interested in that. So if you have X like this, then the derived cohomology of X is canonically isomorphic to a cyclic periodic cohomology of the category perf of X. And therefore, this periodic cyclic cohomology has a canonical Q structure coming from the Betti cohomology of X. So that's not the case for a general triangulated category like this. In other words, we don't know if non-commutative geometry has a Q structure and there are cyclic periodic cohomology. But if the category is geometric, then we do get such. And that may be, an unexpected thing.
What's the subscript on the left-hand side?
Huh?
What's the subscript on
the ROM? The ROM, sorry. So this implies that the periodic cyclic homology of C has a canonical rational structure. Well, that comes from the fact that semi-orthogonal summands in this category are given by Fourier-Mukai kernels, and Fourier-Mukai, of course, acts by its short character on the derived cohomology, and so you can do it.
And how do you know that represented as a component of two different varieties give equivalent Q structures?
Well, I just explained, because it's given by Fourier-Mukai.
What is given by Fourier-Mukai?
So, if you have a Fourier-Mukai functor between d of x and d of y, then this Fourier-Mukai functor preserves the rational structure on the derived cohomology.
So you assume that there is a Fourier-Mukai functor given an equivalence of C embedded into X, C embedded into Y. This is what you expect?
Yeah, but
how do you know that such Fourier-Mukai exists?
well, that's because I'm working in the DG world. So semi-orthogonal summa, I think now I understand your question. So to talk about semi-orthogonal summands, I have to not just talk about, you can define it for triangulated category, but that's not enough. So this semi-orthogonal decomposition should come from a DG level, indeed, and that's important here.
But then you have integral structure, not
No. Well, because current characters have denominators.
So what you have the image of KT.
Huh?
You have the,
Image of
you have the topological case.
you have topological KT, then if you have idempotent, it just breaks into different, and you have image.
Well, you need to explain this to me on the way to JFK. In half an hour.
Not until the first moment.
Okay. So, an important theorem of Orlov says the following. Recent theorem. He says that being geometric is preserved by gluing, so let A be a category which decomposes semi-orthogonally like this. And he says that if B and C are geometric, then so is A. Okay, now our theorem is the following. Let X be a smooth proper Lie-Moffat stack. Then the category of perfect complexes on X is geometry. So let me prove this for you. So the first thing we do, we want to reduce to the case of an orbifold. And as Daniel explained to me, there's a trick you can do it as follows. So you can embed your X as a closed substack in a smooth orbifold. And so this is called smooth proper orbifold. And this is closed.
What do you mean by an orbital?
Orbifold means that generically the stabilizers, there are no stabilizers. And of course that doesn't make the category of X a semi-orthogonal summand of the category of Y, but there is a trick using the blow-up. So now you can, now you know that if you blow up Y along X, by the formula I wrote, this category will be a component of this category. When I write D or perf, it's the same thing. I will be confusing those things. So this is a component of this. And so it's enough to deal with orbifolds. Now what do we do for orbifolds?
So, but if it is divisor, you are doing the root construction instead.
What?
If X has what I mentioned varying by, you do the root construction instead of one with one.
If it has, yes, for example, or you could, make it co-dimension 2, maybe. Okay, so the second step is the following. So we start with our Y, which is now a smooth proper orbifold. I guess orbifold means it's smooth. So proper orbifold. And then you do the destackification. That's just the name of Daniel. I don't know how successful it is. So it's his algorithm. So this is destacking. So this is a composition of stacky blow-ups, and so the category of Y will be a component of the category of Y prime. So it's enough to prove that the category of Y prime is geometric, therefore. Now, what's y prime? You know that if you take its coarse modular space, then that's a smooth algebraic space, and this is rooting. And so we have now a very explicit way to, under this assumption, to decompose the category of y prime, actually semi-orthogonally, where the pieces are the category of y prime, plus the categories of the divisors in which you root, and their various intersections. So in other words, the category of y prime is glued from the categories of very smooth algebraic spaces. So it's enough to show that the category of smooth proper algebraic space is geometric, but then there's an old theorem of motions on that there exists Z, which is proper, which is even projective, and this proper surjective map, which means that the category here is geometric. It's a component of smooth and projective category. So that's the proof. So we use Orlov to show that. Right. So yeah. So we use Orlov to show that to do this step here. Okay, let's see. So now an unrelated application. How much time do I have? 5 minutes. So I will be talking about certain kind of motivic measures here. So let me remind you the Grothendieck Greek of varieties. I think it was already discussed here. Varieties over C. So what you do, you take the free abelian group on isomorphism classes of varieties, and you divide by the relation that the class of X is equal to the class of U plus the complement if U in X is 1. So that's the definition. One thing you notice is if there's X a smooth projective, and you take a closed smooth subvariety Z, when you do the blow-up, then the following holds in this ring, the Grothendieck group. So the class of the blow-up plus the class of Z will be equal to the class of X plus the class of U. So that's a consequence of this relation. So using the weak factorization theorem, that's why we need characteristic 0. Wojenka and Bittner prove that this last part here gives actually a presentation of the group. So Wojenka, let's see. So they say that the same group can be generated by isomorphism classes of smooth projective varieties modular the blow-up relations. And that's the presentation that I like better, because I'd like today to consider measures which will be certain ring homomorphisms from this group. Let's stick to group homomorphisms from this group to some other group. Yes. So I work over C. So let me define the target group that I want to map this to. I'll call this delta. So delta will be the free abelian group on equivalence classes of triangulated categories. And again, I repeat that when I say triangulated category, I mean enhanced, smooth, and proper triangulated categories. So they are all of the form vertical A, where A is smooth and proper. And the relation is the following. So if the class of A will be equal to the sum of classes, if there is a semi-orthogonal decomposition, and again, the semi-orthogonal decomposition should come from a DG level. Okay. Now, the categorical relations for the block tell you that you have a group homomorphism from this group to delta. Let's call this mu. And how do we define mu? So I can take any element in this group and I can write it as a linear combination of classes of smooth and projective varieties by Lunts, or that's always possible, even regardless. So I need to define, so I'll define it for X smooth and projective. So X smooth projective goes by this mu to the class of its category. And Lunts beat the relations plus the relations for derived categories for the block tell you this is a well-defined group homomorphism. Now, again, continuing with the Mackay topic, you can introduce now finite group action. You can consider varieties with an action of a finite group. G it has to be what's called good action, so every orbit is contained in an affine open subset. And you can look at a similar Grothendieck group of such when you cut into invariant pieces. And this group has a similar Lunts presentation. So you have to take X with a G action, and you need to blow up a G invariant closed subvariety, and then everything is just literally the same. And therefore, there is another group homomorphism from this to here. Let's call this mu G. And again, what this is doing, if Y is a smooth projective, then it will go to the class of its equivariant derived categories. Okay. Now, I want to compare these two measures, in a sense. So notice that if X is smooth projective, and the action happens to be free, with a free reaction, then the equivariant derived category on X is equivalent to the usual derived category on the quotient. And since X is smooth projective, this is the value of the measure mu G on X. And this is also smooth projective, so this is the value of mu on X. So if X is smooth projective with a free action, I have this comparison.
Mu on X on G.
I'm sorry, yeah, mu on X. So here's a conjecture of Galkin and Schindler. I'll call this conjecture 1. So for any X, there exists an equality of power series with coefficients in delta, in this group delta, use it. So the left-hand side is the power series, and going from 0 to infinity. For n equals 0, this is just 1. Otherwise, it's mu with the group Sn. So you take the variety x to the n, it has a natural action by the group Sn, so you take the equivariant measure applied to that, right? And that's the coefficient of t to the n. And on the right, what you take is the product. It's a little complicated, but I'll explain. I'll write it differently in a moment. So it's a product of infinite sums. So this is the now mu, the usual mu applied to the nth symmetric power of x, right? And this is the coefficient of t to the n times L. So maybe a comment here. So what if I just look at the inside here without the mu? This is called the motivic zeta function. So for any variety x, you have this power series, n equals 0 to infinity, and sim n x times t to the n, right? I should write a class of this. So that's an element in the power series ring with coefficients in the both and the ring of variety. So that's called the motivic zeta function. So you can write it like this. It's a product over L greater or equal 1 of just the measure mu over there applied to the motivic zeta function of x, but you change the variable to t to the n. That's what it is. All right, so let me be a little more explicit. So I'm going to prove this. Well, maybe not. This is what we can prove. That's a theorem now. But so explicitly, what is the right-hand side explicitly? What's the coefficient of t to the n? So explicitly. So it says the following, that this element, that's the coefficient of t to the n on the left, should be equal to the following. It's a sum over all partitions of n. And by partition, I mean that the sum of alpha I times I is n of various products of symmetric powers. That's what, this is the coefficient of t to the n on the right-hand side. And let's rewrite this.
So you probably want to apply mu on the right hand side.
Yes, thank you very much. And notice that, so even without the mu, so so if I remove the mu, then it's equal to the following. It's the sum over all conjugacy, over all representatives of conjugacy classes of Sn of the following. So I will take mu, since it's there, but it's true without the mu, apply to, I'm taking x to the n, and I take a fixed point set for the action of this element, and then I divide this by the centralizer of this element. So that expression may look familiar to many people, like doing orbifold cohomology and stuff like that. All right, so now let's look at what's conjectured here. It's conjectured that this is equal to that. And so the second conjecture of Galkin and Schindler says that the group Sn is irrelevant here. So their second conjecture is an equality here for any.
Can I just ask?
Yes.
If x is a smooth
Huh?
surface, if x is a smooth surface, you can introduce the slings.
No. Let me. That's a good point. So, let me comment on that. So, you would like to remove the measures here and have an equality of power series with coefficients in the ring of varieties. Yes. And so, since you know that this category is equivalent, so you know that if X is a smooth surface, right? Then the Sn equivalent category of X to the n is equivalent to the usual derived category of the cube. And so the temptation is to remove the measures and take your coefficient of cube n, right? And you ask, is that a correct equality? Well, the answer is no, because there will be some extra L's. L is a class of line appearing where it shouldn't appear. But that's fixed by our measure, because our measure, n, mu, sends L to 1. And so that makes it true. But
there is some true formulas with that.
Expresses left-hand side explicitly in terms of right-hand side with some concessions.
well, maybe you can, you know, you can distribute the L's so that it works, but that's an, I'm saying.
It's a very old theorem, proved by Götze and Bergh.
What I'm explaining now is that something is wrong, and I'm saying if you take cube and use it as a coefficient, it's not true.
Right modulo L. Modulo L minus 1.
Yes. Okay, so yeah, but that's another interesting question. Can you sort of remove the measures, and is there something, is there some identity in this passage? Okay, so conjecture 2, again, by Dawkins, Schindler, is the following, that for any x with a finite group action, mu g of x is this sum on the right side. So sum over all conjugacy classes, mu applied to. So I'm just taking that and writing it for general proof. Now let's look at this conjecture. This is a very fascinating, strange conjecture, I would call it, but amazingly it must be true. So why is that a strange conjecture? Let's look at.
And do you expect a semi-orthogonal decomposition?
Well, X is here any variety, not smooth, not. So.
But for smooth varieties, do you expect a semi-orthogonal decomposition?
Well, all those quotients need to be smooth, right?
Of equivariant categories. You can take G equivariant category on the left-hand side.
Yes.
Does it decompose into a number of Z G equivariant categories on the right-hand side?
But for this to be true, those spaces have to be smooth at least. That's what I'm saying. Huh? Well, if X is a smooth projective, right?
What's the cases one on the top one with X equal?
Same component of saturated category saturated, right? So it has to be smooth also. Those quotients. So, right, in terms of all the semi-orthogonal decompositions, the statement becomes more subtle, and it's actually conjectured in some cases, you're right. But when you pass through this Grothendieck group delta, you can make sort of a simpler statement. That's it. So let me give an example where X is just a point. So what do we have? So group Gx on a point, so what is this measure? Point is smooth projective, and so this is just a derived category of G equivariant cubes on a point. That's a representation theory of G. And so the left-hand side just measures the number of irreducible representations of G times 1, if you want. 1 is a number. Okay, but what do we have on the right? Well, on the right we have the number of conjugacy classes of G times 1. So the two numbers are the same, but there's no bijection between the two sets. So that's a fascinating part in this conjecture. Tells you that things cannot be very easy. So the theorem is now that, as I showed here, this first conjecture of Galkin and Schindler is equivalent to a special case of this one. It's equivalent to that, which is So in the special case, we can prove this conjecture 2, and therefore conjecture 1. Conjecture 1. So what are the ingredients of the proof? Well, the sort of most important ingredient, which just doesn't work, I don't know how to do it without Daniel Bergh's theorem, is the following. So suppose G acts freely on U, but U is not smooth or projective, it's just anything, right? Then the claim is that nevertheless the equivariant measure of U coincides with the non-equivariant measure of the quotient. So this is a fundamental fact which allows you to approach this conjecture by actually cutting your varieties into pieces, because the categorical measures are only defined globally, but this allows you to compare things by cutting. And so let me write here a diagram. So you've got K naught of varieties, K naught of G varieties, and here is the group delta, and you have those homomorphisms, group homomorphisms like this. Now let's try to fill the middle of this diagram here. So let's introduce the group K naught prime of Deligne-Mumford stacks, so that there will be arrows like this. And what is this? Well, that's the group of generated by smooth and proper Deligne-Mumford stacks modulo the stacky blow-up relations. So it's an analog of bit representation of these two groups. So generated by smooth and proper Deligne stacks with stacky blow-up relations. Okay, and then the formulas for semi-orthogonal decomposition, which I will tell you that there is actually, you can close this diagram, there is a measure, similar measure here, which I'll call mu dm, which will take a smooth projective here and assign a class of its category in delta. Now, there is a homomorphism from this group to something that you may call K naught of dm, and that group is defined in the usual way when you cut Deligne-Mumford stacks into closed and open. Okay, so this is usual. But we don't know if this diagram can be closed by a homomorphism like this. Right. Now, if we knew that there's an arrow like this, then this equality would be a triviality, because you take U in here, and you look at its image. You look at its image here, and its image here is just equal to that, because as stacks with a G action, U is just isomorphic to G. Right? So these would give you the same element here, and then that would be a triviality. But since we don't know that, some work has to be done. But Daniel's technique says it suffices to have this diagram without this arrow, and then do stacking modification to prove that it holds. So this is the main input. And the second ingredient is the following. So how do we prove this conjecture in the second conjecture in the special case? So what suffices is the following. So suppose you have a group G, which is a real product of Sn, acting on a product of some, just a power of some other abelian group A. I'm sorry, is that the correct way? Like this? Okay. With product. And suppose that this with product acts on some variety X via its quotient Sn. Then the category of G equivariant sheaves on X can be understood as follows. It is the category of Sn equivariant sheaves on the following space. You multiply X by a discrete set which is the irreducible representations of A to the n, sorry. And so notice that Sn was acting on X because G was acting on X through Sn, and Sn also acts by conjugation on this normal subgroup, and therefore acts on this set of irreducible representations, right? And the second fact is that the two Sn sets, one is irreducible representations of An, and the other is conjugacy classes of in An, are actually isomorphic. So these two strange facts, accidental facts, allow you to prove this special case, allow you to prove this. Now, if you try to prove the general case of this conjecture 2, then this is false and this is false. So somehow we have two wrong steps which combine together to give the right step, but I don't know what
do you mean by saying these steps are false?
Huh?
What do you mean by saying these steps are false?
Well, there is not such equivalence of category.
What does it mean?
Oh, so you can consider just any G with a normal subgroup, and G acts on some X through the quotient. Right? So you can consider that's the case to be understood. All right. So just two quick things to finish. Let me give maybe a proper formulation of conjecture 2. So let me call this conjecture 2 prime. So as the following: suppose X is a smooth and proper DM stack, although that shouldn't be important, but just because I don't know that my measures are defined, such that the inertia stack of X has a coarse modulus space which is a scheme. Well, I don't really know how restricted, how important these assumptions are. Then the categorical measure dm of X coincides with the usual measure applied to the coarse modulus space. So that's a. So if you do this for global quotients, you refer to the second calculation of conjecture, but that's, I think, is good. So and the last thing I should say that this second calculation of conjecture is known if you are not so picky with the domain. So remark this. I've defined this group delta. The group delta of categories modulo semi-orthogonal decomposition. This is a very fine relation, maybe the most fine sort of motivic relation you can impose. But there is a group homomorphism from this to K naught of tabuadas non-commutative motifs. So here you allow much more flexibility. So morphisms here basically is a K theory of the product. So you have many more projectors here. So K theory is K naught of the usual charm motifs embeds here as a full sub. So this charm motifs embed as a full subcategory here. So, and you know that any additive invariance of your category, they're factored through here. So for example, K theory or functional homology factor. And Galkin-Schindler conjecture is known if you compose homomorphism from delta to any of the additive invariants, and even to here, I think. But theorem claims it's true even here. So we're trying to lift it to this line. I'm sorry, I'm 1 minute over. Thank you very much.
Well, Professor Lunts has to leave very soon, but maybe if there's a quick question.
I mean, there's this equidal variant of stacks and some localization. You must know about that? I don't know if it's related.
So equidal says that the growth in the group of Artenstedts is the localization of the growth in the group, right? But there you invert too much from my perspective, because you invert anything, all polynomials like this, I think, right? And in particular, you invert this. But as I said, my categorical measure sends this to 0. So yeah, I kind of. That's for the lemma for which you work.
Well, if there are no other questions, let's thank Professor Lunts again.